Hello and welcome to Intro to Calculus. So today we'll be starting at the very beginning with the limit. So things we'll be covering today. Basically, what is a limit? Not going to go into any details, nitty-gritty details on how to calculate a limit, but I'll basically talk about what a limit is. And I'll also cover the basics of the tangent line problem and the area problem that define a lot of the introductory calculus. And then next week, we'll get evaluating limits analytically, so actually solving the limits. So let's start by imagining a graph of a function. Let's call it f of x. So we have our function f of x here, and we want to know what this function looks like at x equals a. Here we can see the function is clearly defined at x equals a. So if we want to know what the y value is, we just say f of a, and this will give us our y value at a. But in some cases, it won't be as clear cut as this. Imagine now that our function f of x has a discontinuity at x equals a, meaning it's not defined at x equals a. So the function's defined up to here, but it's not defined at that specific point. How would we figure out basically what the function would look like if it did exist at a? So how we do this is we look at this function and we say, all right, what is this function getting closer to as x approaches a from the left side? And what does this function get closer to as x approaches a from the right side? So in some cases, you'll see that if I want to draw a table here, say we've got our f of x, right? We've got like x equals a minus 1, x equals a minus 0.1, x equals a minus 0.01. So we're getting closer and closer to a. And then let me create another table of f of x. We start with x equals a plus 1 and move to x equals a plus 0.1, and then x equals a plus 0.01. You see, with each successive step, we're moving closer and closer to x equals a. We can fill out our value. Let's say our value is 0.85, 0.89, 0.899, and then here we get 0.95, 0.91, 0.90. We see that as we get closer and closer to a from the right side, our value seems to be approaching 0.90 or something close to 0.90. Here we look, and we're going from the left, and as we go this way, we see that our function is approaching 0.899. So we can look at this and say that if the function is getting closer and closer to the same value right here, we can say that if the function did exist, this is likely the value that it would exist at. So the way we write that is lim for limit is x approaches a. And this here means as it approaches a from both the left and the right, meaning it has to approach the same value from both sides. Let's say we had a graph here. We had a function f of x that looked like this. this function, does it have a clearly defined limit at x equals a, here, a equals x? So look here from the left, it's approaching one value, but from the right, it's approaching another value. So if it were to exist, if there weren't a discontinuity here, would we know where the function would most likely be? We can't tell in this case because the left limit and the right limit don't approach the same value. So this here is the limit from the left and the right both combined. If they both approach, and this is our function. So the limit as x approaches a of f of x is equal to L. If this is true, so if this value, say, is L, we see we're approaching a value L from the left and from the right. We say that the limit as x approaches a of the function f of x is equal to L, or the value that it approaches. So that is the basic definition of the limit. And I will run through a quick example before moving on to the tangent line problem. Let me leave our definition of the limit up there. So, let me draw a graph. We have, say, f of x equals x squared. What is the limit as x approaches 2 of the function f of x? So what we're looking for is, say, this is x equals 2. We're looking for the limit from the left and the limit from the right to see if they approach one value right here. And as this is a continuous function, f of x is x squared, this value should be 2 squared, which equals 4. So this should be 2, 4 right here. So if we were to make a table of values here, we have right in here, let's choose 1.5, 1.9, 1.99, and 1.999. So what we need to do is plug each of these values into the function to see what it gives us at that point and to see if there is a clear trend. Now, I don't know how to square these numbers in my head, so I'm going to plug them into my calculator here. So we have 1.5 squared is 2.25. 1.9 squared, 3.61. 1.99 squared, 3.9601. And 1.999 squared is 3.996001, but I won't write those extra values. Now, let's take the limit from the right. Let's say 2.5, 2.1, 2.01, and 2.001. So we take 2.5 squared is 6.25. 2.1 squared, 4.41. 2.01 squared is 4.0401. And 2.001 squared is 4.004. So you look at both of these tables, 3.996 from this way, and then from the right goes all the way down to 4.004. You can see that this function does look like it is approaching 4. So we can say the limit as x approaches 2 of x squared is equal to 4. And this is consistent with our currently known value of f of 2, which is 2 squared, which is equal to 4. Now, in the next video, I'll go over more complicated ways of solving for these limits. But for now, this is the general idea of the limit. Now I'm going to go over the two of the big problems that we use the limit to solve in calculus. This will serve as pretty much the basis of our entire intro to calculus, the tangent line problem and the area problem. The first one of these is the tangent line problem. So I'm going to draw a graph, f of x. And let's say we wanted to know the slope of the line at the point x equals a. Well, if you remember from algebra, in order to take a slope, and the slope is equal to the change in y over the change in x, which is y2 minus y1 over x2 minus x1. In order to take the slope of a line, we need 2 points. So we can approximate the slope of the line at point A by adding a point here, B. Then, when we draw the line through that, this is an approximation for the slope of the line at x equals a. But this here isn't a great approximation. We can make this approximation better by moving the point B to, say, here. Then, we've got a new line here, which is a better approximation for the slope of the line at this point. But let's say we want to get a little better. We want to get a better approximation. We move the point to, say, here. And then we get a better approximation for the line. Now, we can let these 2 points get really, really close together to the point where they're so close that they're almost right on top of each other. So what we can do is we can essentially take the limit as the change in x values between these 2 points gets smaller and smaller and goes down to 0. So the value of the function here, the y value of the function at a, would be f of a, and the y value here would be f of a plus our change in x here, and that's because the x value here, which we call b, would be a plus the distance between a and b. So f of a plus delta x. So we know the slope of this line here between a and a plus delta x, or b, is change delta y, change in y, which is f of a plus delta x minus our original y value, which is f of a, all over our second x, which is a plus delta x minus our first x value, which is a. And from this, we get the slope of this line is equal to f of a plus delta x minus f of a all over delta x. Now we can take the limit as delta x approaches 0 of f of a plus delta x minus f of a over delta x to get what the slope of the line would be at that point. And this is the basis behind the derivative, is taking the limit of the slope of the secant line as the distance between the points goes to 0. Now the second problem, this one is the basis behind the definite, both the definite and the indefinite integral. This is the basis behind the integral, is the area problem. So in algebra, you've been taught how to take the area of a rectangle of length L and width W. The area of this is equal to the length times the width. Let's say you wanted the area under a graph, say, we've got a function f of x. You want the area under this graph from A to B. We don't know how to take the area of this odd function, whatever it is, because we don't have the general formula for it. But we can approximate the area by drawing a rectangle here, which we know how to take the area of a rectangle from algebra. And we can draw another little rectangle here, another little rectangle here, another little rectangle here, another one here. We can take the area of these 5 rectangles and we can sum them up to get an approximation for the area of under the curve. But you can see, like, right here and right here, there's spots that stick up above. Right here, there's a little spot that sticks down below. So it's not a perfect approximation. But as we did with the tangent line problem, we can make this better by making the rectangles smaller. This way, it's a much better approximation. Let me split this one a couple of times, draw the new line here, new line here. And as you can see, just from making these rectangles a little bit smaller, the amount of discontinuity that we have, the amount of excess or lack of area, is gone down slightly. Now let's say we wanted to split these rectangles in half again. It would make an even better approximation. So what we can do, is we can take the limit as the distance between these rectangles goes to 0, which in many cases is as we let the number of rectangles approach infinity. So limit as delta x approaches 0 of the sum. Now let's see the area of a rectangle here. We have our x value x of I, and then f of xi is our y. So our area, ai, for the ith rectangle is equal to f of xi times whatever this delta xi here is. So we can take the sum. We can add area of area 1 plus area 2 plus area 3, so on and so forth, area n, to get the area, say, from I equals 1 to n. Now, as I said earlier, when we let delta x approach 0, as the rectangles get smaller and smaller, oftentimes, in most cases, the number of rectangles will approach infinity. So I'll rewrite this as n approaches infinity. So as we keep drawing the rectangles smaller and smaller and smaller, we get less and less and less error between each one. equation. This here is our, this should be an F, not an A. Sorry about that. But this here is just our equation for the area. So as the number of rectangles get smaller and smaller, we take the sum of all of those rectangles. And this here will be area under the curve. And this is the basis of the integral. Is that we take and draw a bunch of rectangles and make them smaller and smaller and smaller until the number of them approaches infinity. And we take the limit as the number of them approaches infinity to get the area under the curve. So that's going to do it for today. Next time, we'll be talking about evaluating limits analytically. I'll go into a little more depth on how to solve for the limit of a given function. And then after that, we'll move on to the introduction to derivatives. Thank you for watching. Hope you have a great day. And cut.